Okay, Henrik and I have worked on something like a strategy to explain what you need to know to start the static alignment adjustments of the NeuroSwing on the patient while standing. First of all, it is important to distinguish between the ability to stand or not to stand and what that actually means. Now, Henrik was against it, but I wanted to show you this example because this little pony is always on the desk of our colleague Almut. I think it is a perfect way to explain and introduce the distinctive characteristic of bipedal standing. So the pony stands or has the ability to stand on four legs, and that is very easy. There's the center of mass in the middle of these four legs, and the horse will not fall over. That's pretty easy to understand. How does it look like when someone is standing on two legs? Okay, that is a little more complex, and for this reason we have given some thought to this. The alignment of an orthosis should of course be checked once on the workbench before we go to the patient and check the static alignment. How it works is explained in depth in the online tutorial. We described that the vertical plumb line from the center of gravity through the middle of the AP should fall in the front half of the supportive area. These are all very nice words, but what exactly do they mean? What is hidden in this terminology? The supportive area in this case is actually the foot. The foot significantly increases the supporting area for us bipeds and thus enables us to stand on two legs. But for our patients, who are usually not able to move their toes, this is a very special situation, and thus we have to explain which is a supportive area available for the patients a little bit more precisely than in the physiological sense for bipeds. Because in this case, the support surface does not include the entire length of the foot, but it is limited to the distance from the heel edge to the highest point of the roll-off area. This is the reason why we have to build in a toe spring in the orthosis. This is in order to create an ideal dynamic condition for our patients. If we were to build an orthosis for standing only, we would do it without a toe spring. But of course, we don't just build an orthosis for standing. We build it primarily for walking. For this purpose, it is important to understand that the supporting area that is available to us orthotists is limited between the highest point of the rolling area and the heel. To recognize the front half of it, that's pretty easy. We divide this area by 2, and if the center of gravity line from the mid-AP falls into the front half, that's not bad. However, to create ideal conditions for the dynamics, it makes sense to align the plumb line exactly and as physiological as possible. That means it makes sense to drop the plumb from the center of gravity through the mid-AP so that it falls into the area that's hatched here. This limits the area through which the center of gravity should be supported much more precisely than just saying on the front half. The question is, how do I know or how to identify this hatched area? To explain this, we took out the insole of the shoe and traced it on this cardboard as an example and then made some drawings on it. On this sole, we marked the highest point of the roll-off line and the end of the heel. We marked here in red and divided the available supporting area into halves. Now, in order to delimit the hatched section, we divide this area shown here in green into 3 parts. 1/3 is in front, 2/3 in the back. We take the second line that divides the front third and the midline, and this small area that lays between the 2 markings is quite exactly the place where the plumb line of the center of gravity should fall. As said before, we have divided the forefoot area, the forefoot lever, and the heel rocker lever arm into rather ideal ratios, which is certainly good for the dynamics. However, we would like to explain to you once again with another example what this means for the statics, so the term stability takes some form. For this reason, we have reduced the patient to the most simple object of all. We have taken a broomstick to hand and have simulated a body center of gravity, which has been marked here. We want to ask the question if this broomstick, which is standing next to me, is actually able to stand or not, or what happens to the broomstick next to me. Let's try. If you drop a plumb line from the center of gravity of your body, we see that the plumb line falls between the end of the broomstick and me. That means, at this moment, I am an active part of this whole structure and provide stability to the broomstick. As a result, if I go away, the broomstick falls over. It is not able to stand on its own. You could say that the alignment of the broomstick was far from ideal because it was so slanted. But even if I idealize the alignment and stand it straight as a candle, the broomstick will fail to achieve the stability simply because the support surface that is available to it is way too small.
Ein stabiles Gleichgewicht für den Besen zu erzielen. Ganz einfach,
now, the solution for this problem is obvious. We have to increase the supporting area, and that is exactly what we will do. Here we would do it also for our patients. We are showing how we increase the support area available to them. Here it is simulated by a cardboard shoe. We expect the plumb line to fall between the body's center of gravity and the available supporting area. And we see that we have achieved that, and it is stable. The broomstick can stand stable without my intervention because we have extended the area of support, and this will provide more stability.
Eine größere Unterstützungsfläche zur Verfügung gestellt haben, die nutzen kann für
In the meantime, Henrik has already put his orthosis on. So now we can check what was just discussed directly on the patient. That is, the difference between being able to stand and not being able to stand steadily.
Und nicht stehfähig wollen wir einmal besprechen.
Okay, we have aligned the orthosis statically on the workbench to a basic setting. The plumb line falls from the mid-AP measurement on the hatch area. Everything looks great, even if we follow the vertical line upwards. It falls through the hip and through the center of gravity. That means he has an ideal bench alignment. However, as we have just learned with the broomstick, the ideal basic alignment is not everything we need. The next question would be, can he also use the supporting surface that is available? That is, if he were to stand in a less ideal position, for example, with a flexed knee, because his knees are not straight, perhaps due to a flexion contracture, would Henrik be able to stand despite the less than optimal alignment?
Einfach nicht gerade bekommt, er hat eine Flexionskontraktur. Ist die Frage,
I would definitely say yes, because the plumb line from the body center of gravity is still falling on the previously marked place on his foot.
sich das Lot immer noch zwischen seinem Körperschwerpunkt
Even if the knee axis is not in the right position in relation to the plumb line of the center of gravity, it's still a stable standing position, and certainly an alternative way to find a stable posture whilst standing. We would say the necessary balance is provided. Another position that we observe is when patients have hip flexion contractures. In this case, the tibia is not in a physiological inclination. The upper body is forced to move forward, while the buttocks are stretched backwards to achieve some stability over the supporting area. The question again is if Henrik can stand at this moment. Yes, absolutely, because the plumb line from the body's center of gravity falls over the marked area on the foot, and therefore he can achieve stability in standing. So, if Henrik would now feel the need to move the crutches forward, let's say in order to artificially increase his base of support, then we would know that the device or orthosis we have built has basically missed its target and it's not doing what it is supposed to do. It is not able to give Henrik the stability that he needs to feel safe. That means he puts the forearm crutches far in front of him and becomes a four-legged animal like a pony. The plumb line from the center of the body falls between his feet and the crutches. In this situation, Henrik would not be able to stand upright according to our stability concept. And we should definitely not only check the static alignment, which we did before on the workbench, but we should also consider whether the spring used here in the front is really strong enough to apply the required extension moment to stabilize the knee. Of course, we would have to recognize that some patients stand in this position habitually, and then it would make sense to encourage them to rely more on the orthosis and to feel the support that's given to them through the ventral shield. They can lean against the ventral shield and bring the forearm crutches closer to straighten up the upper body. We should check if it is possible for them to assume a more physiological position and to take the load from the crutches and, of course, from the wrists and the shoulder joints. What we are trying to achieve is a more physiological posture that could provide more stability and balance and improve the walking ability of the patient. Okay, now what's next? Henrik, what else did we want to check? We definitely wanted to check how we can recognize the resistance of an orthosis if we look at the whole thing again from the front. From the side we have done some tests, we have looked at whether Henrik was able to stand stable in the orthosis or not. Now, looking at him from the front, we should of course check if the patient can transfer the weight from one side to the other, that is, from the contralateral side to the orthosis side and vice versa. Before letting the patient take even one step, it should be checked if the patient is able to put weight on the orthosis and ideally to stand on the orthosis. To test this, It is not necessary to lift the feet from the ground. The patient should simply shift the weight like we are demonstrating here, and this should be sufficient. If we now look at Henrik again from the side observing the sagittal plane, we can talk about what we were thinking of before starting the dynamic alignment of the NeuroSwing on the patient. Once again, why do we prefer this idealized alignment where the center of gravity line passes through the middle of the body, the hip, mid-AP at the knee, and the hatched area on the shoe? The reason is not only that balance is provided in standing, but also that a physiological position is achieved which corresponds to the position at mid-stance. Here it is shown by Henrik, comes very close as you see. Okay, this would mean that we are creating ideal conditions for the dynamics by idealizing the alignment, which will definitely help to reach the goal that we have in mind. Okay, all other alternative ways of standing for the patient are also, of course, possible, but certainly do not lead to the optimal biomechanical conditions for a dynamic gait, and do not fulfill the requirements for the patient to be able to walk. They do not support the patient's ability to walk in a physiological sense. Now we have to change the room and we say goodbye for a very small break before we continue with the dynamic adjustments of the NeuroSwing on the patient.
Mit der Einstellung des NeuroSwings dynamisch am Patienten.